All right, so let's look at the following exam. So this is coming from your textbook. It is a problem, in fact. So in Taylor and Carlin on page 69, right? Okay. So, okay, we are given a sequence of IID random variables. Okay, so let x1, x2, and so on are all IID, positive random variables, whose common distribution function is f. Right? So we also know what their distribution is. We interpret x1, x2, and so on, these random variables, as successive bits on an asset offered for sale. Right? So you might have a house, a car, let's say, right, to sell. Right? So you put an advertisement in the newspaper, right? So then your phone starts ringing, right? You pick up phone, and everybody gives you a bid, right? So they will say that I would just pay such and such Turkish liras to purchase that house or car on sale, right? So these bids are coming, right? So you have to make your mind when you would like to sell the car finally, or the house, right? So suppose that we decided to accept the first bid that exceeds some prescribed number A. So you have more or less a figure in your mind. So you say, for example, well, this house is worth 300,000 Turkish liras, right? So it's a fancy house, let's say. Okay. So you are willing to sell the house to the first guy who bids something at least as large as 300,000. So that's your A, a constant. You fix it, you put it aside. Right? And what would like to calculate? Let me see. Okay. So then the accepted bid is going to be denoted by x sub n. So I have to now write all these things once, I guess. So let me start from the beginning. So these are all successive bids, right? All right. These are all successive bids on an asset on sale, right? We assume that all of them are, well, these are independent and identically distributed random variables with common distribution function f. So we assume that f is also known, all right? And then we agreed that we accept the first bid, right, greater than or equal to some number A, right? Right? Okay. Then the accepted bid, right, is going to be, how would you denote it? It's actually a composition of two random variables, so x stopped at some random time n, rather than a fixed number 1, 2, or anything like that, where n is defined as the first time, right, the first bit xn, which is strictly greater than a. I guess I am going to look at the strictly greater than case, right? 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 So where, right? N is defined like this. So n is basically the time when you sell, right, the asset that you have, or basically it is the same as the time when you accept, right, a bid, right, the first bid, the very first bid, right? And then the size of the bit is not necessarily A, right? Because somebody, you don't know, anybody on the phone will not actually know how much large a quantity that you are looking for. They will just give you a number. And if it is bigger than A, you will just be happy, right? So you are not going to turn away that and just return the remaining part. So we are in this question interested in, on average, how large this quantity is going to be. So you are going to wait until you hear a bid which is at least as large as A, and then, right, at the beginning you would like to know what the actual payment is going to be, on average, right? So we would like to, but there are a couple of questions. First of all, right? This was part B. So what is on average your payment is going to be in this case, right? And we will actually look at revisit this problem. If you know that x1, x2, all these bits are IID exponential random variables, so we'll do some more concrete calculations. We will get a general answer in this second part, and in the last part we would like to just get some concrete numbers or more concrete expression if lambda is just a general quantity, right? But in part A, the very first question that may come to your mind is, well, do we ever have a chance to sell this thing at all? You may just wait and wait and wait, and you may actually end up not selling this asset at all. That may also happen, right? What happens, for example, if A is so large that nobody really is thinking even to offer a number or a bit which is even larger than what you have in mind. So we would like to now also ask the question, before we really worry about all these any of these things, right? The probability that the asset will be sold, will be eventually sold, right? A bit positive probability, you know that you cannot sell this asset, then you have to be careful. Maybe you would just revise this quantity, right? The condition, we will be answering all these questions under the assumption that the probability that one of these bits is greater than A, which can be written, right, as this probability, if, well, in terms of the cumulative distribution function, is positive. That actually immediately gives the answer for part A, but we have to just gather all our thoughts to answer the problem, to solve the problem. Right? Are the questions clear to all of you? Huh? Huh? Okay. So, okay, what is this random variable? Well, okay. Here I did not elaborate on that, but it is like, okay, if it is a random variable, right? So for each omega, this should have a value, but as I said, this is nothing but just the composition of these two random variables, right? So n omega happens to be, or I guess just write like this. Let me do that. So it is like, okay, on the event, n equals small n, x capital N equals to xn, right? So that's how you should understand what we mean by this, right? Whenever, if you happen to accept the nth bit, then of course xn equals x little n, which is natural, right? So that's, actually we are not introducing anything contrary to our intuition. Okay. All right. And in part B, now before we calculate anything, let's just try to use our intuition to come up with some answers for this one. For part A, what is the probability that we will eventually be, this asset will be eventually sold, right? So how should I look at this problem? So every time, right, you are getting successive bits. What is happening every time you get a bit? You will either be successful in meeting a bit which is greater than A, that's what you want, or you will fail in getting a bit which is as large as what you expect, right? So this is again like what? There are repeated experiments, right? In each of experiments you are only interested in the result. Either it's a failure or a success, right? So again we have what? Before that, we have Bernoulli Trials, right? 0-1 outcomes coming up, and they are independent. The result on one outcome doesn't affect the result of the other because bits are independent of each other. So these bits are going to be greater than or A or less than A independently of each other. So if there are failure on one bit, if that bit fails to be greater than A, it doesn't contain any information about what will happen on the next thing. Right? So they are independent. So the Bernoulli trials are independent of each other. Do they have common distribution? Well, for a Bernoulli random variable, all that really completely specify the distribution is a success probability, only one single number. And in this case, success means that a bit is greater than A, right? So success probability, P of our Bernoulli trial is the same as the probability that a given bit is greater than A, right? And the bits are independent of each other with the same probability distribution function, F. If probability distribution function is the same for all of these bits, the probability that any given bit is greater than A is going to be the same at every time, right? So all these Bernoulli random variables are then what? Not only independent, but also identically distributed with the same success probability. So then what is happening? From our point of view, right, as the owner of this asset, we are actually conducting independent, identically distributed Bernoulli trials. And what are you interested in? And which is defined as least time, right? The first least, right? The minimum, that means the least time you get a success, right? So what kind of a distribution do you think n must have? Geometric, right? The time of the first success, right, is in the sequence of IIV Bernoulli trials must have a geometric distribution, right? Right? So we hit all these things. So we know that n now has geometric distribution with success probability. Let's denote it by P again. Defined as what? Any one of them, just the typical, just choose one of them, right? Because they have the same distribution. It is greater than A, right? Or this is what? 1 minus the cumulative distribution function of random variable x1 evaluated LA, right? And if this is true, we assume that is true. Now we have a positive, with some positive probability, in any one of these trials, we will get a success, right? So I did not write the details, so you got it, right? So again, in this problem, there are Bernoulli trials embedded somewhere, right? Either bits are smaller or larger than A. They are all independently identically distributed because the results depend on independently and identically distributed random variables x1, x2, and so on and so forth, right? And n is just the first time you get a success, and therefore it is geometric, and the success probability is related to the distribution function of the underlying bits like this, right? Right? And now we are closer to giving an answer to part A. So so forget about the probability. First look at the event again. So the event that I said, right, will be solved eventually. That's again in words. So how can I write this in terms of random variable? I guess n in this case. This is the same as writing what? Huh? No probabilities. I haven't come to that point yet. So it's just an event. So I'm looking for an equivalent way of writing this bunch of words too long, right? So, write and speak the same thing. So that should n equals little n. That's a starting point. What is n? This is like 4, 5, 6, 17. Do you care about n, really? For some n, right? That's what you want to say. That there is some finite n for which this capital N equals, right? It is like actually probably you would put a union here. Okay? You don't care which one. For some n, right? For some n means, so for some capital N equals to n, for some n means basically some of these events, one of these events will happen, right? Even there is a simpler way of writing this. This is true. This is great, right? Actually, you just say that n is finite. All right? Now, I know that in your calculus courses, you never deal with numbers like infinite. But they are not scary things. They fall out quite naturally. So you should be able to, in this course, you should be able to think in terms of these events. N equals plus infinity means you will never be able to sell it, right? And that's a dangerous thing, because let's say, okay, so you have some retirement fund and you purchased a small piece of land, hoping that its value will go up, and then you will make a living when you come to 60s, 70s, for example. But if you make a very bad investment decision, and if there is a possibility this event can happen, then that means like a sunken investment. You will not be able to get your money back, right? So you should be worried about that this event may happen. And therefore, we add to our set of interesting events. You remember there was this script F at the beginning. These events will be there, and we will try to put actual probabilities, or we will try to understand what the likelihoods of these events are. And we actually face a similar problem here. So what is the probability that eventually we will be able to sell this asset, right? That's intimately or ultimately related with this investment or sales marketing strategy, right? Some marketing strategy. So you will be asked to find NA, specify NA, so that your profits are going to be handsome and so on and so forth. And before that, you will be just asked for whether this is a sensible or reasonable sales strategy or not, right? Right? One way to really argue, or one way to really judge that, to just ask, what is the probability that this will happen, right? If it is greater than, if the probability of this event, now we can just go to probability. So now, if the events are the same, of course, probabilities must be the same. So what in the first part you are interested in is the probability that n is finite, right? Now, can I calculate this? Or do you have an answer? Perhaps I don't even need to calculate. I probably have the answer already. And this is a probability involving, well, of an event involving n, for which you already know the distribution. So n has geometric distribution. What is the probability that you will wait indefinitely long in order to get the first success? Have you ever thought about that? If p is positive, it is 1. That means you eventually will get that. So there is no danger of like losing money on this. But as long as you are willing to wait long enough. So we don't even talk about inflation here. We don't have that yet. But if you want to really convince yourselves that this is the case, well, actually you would indeed use this equivalence, right? So this event equals to that, and all these things are, again, disjoint pairwise disjoint. So the probability of this event is the probability of the union of disjoint sets, and the probability of union of disjoint sets, pairwise disjoint set, is the sum of the probabilities of those sets, right? So you have that, right? We always have that, from 0 to infinity, right? Right? And then, what do you have? 0 to infinity, because n is a non-negative random variable, so I don't care about the negative values. Right? And, well, we said n has geometric distribution, so you remember the way we derived it. So having the first success on the nth trial is has the probability what? You must have n minus 1 failures before, each of which will happen with probability 1 minus success probability, right? P is success, 1 minus P, failure, right? Probability. All, we said, well, these are all Bernoulli trials which are independent of each other, so therefore you take 1 minus P, multiply with itself n minus 1 times. So this is the probability of having n minus 1 failures, and then there will be the first success coming right on the end trial with probability p. So now this formula takes care of that. You sum over n. Well, p doesn't depend on n, so it goes on. Well, it is not actually okay. Even if this is true, which is not actually, you have to, in order to get this a success, you have to try this at least once. So the sum should start from 1, in fact. Okay, in this case. And if you forget about this, it went out. So this is not from 1 to infinity. It is just a geometric series, and it is 1 minus the number sitting here. It is this, right? And I can do all of this, right? And then you have p over p, which is 1. Okay? I have that. Okay? So we now we are safe, right, with this project. So we know that eventually we will be able to sell this asset, and then you're now interested with this more interesting question. Right? Knowing the answer of this more crucial question. Well, okay, I said level at A. What should I expect on average to get paid at the time when I sell this asset, right? I need some estimates. What do you think this quantity? This quantity should be at least as large as A, right? Because you don't sell otherwise, right? That's great. Anything better than that? Or more accurate? No numbers are, so whatever you say actually should somehow be related with F or something else. Actually, perhaps with a conditional expectation. I know this is difficult, so I'll just write it. And then you will think that it makes sense. So this is the same. We will show that this is the same as conditional expected value of x1, right? Given that it is greater than A. Right? Because you know that you sell only when x is greater, a bit is greater than A, but then you don't really have any further information. That's all you know. What you know is you will sell at the first time somebody offers a quantity at least as large as A, and you don't know nothing more than that. So on average, then what can you expect to gain? Well, the expected value of any one of these guys conditioned on now I know that it is greater than A. That's all. Right? Right? So we don't even need to do any calculus, right? So when you start thinking like this, then you will be able to just write down the answer. Okay, that's also part of our. So you should be able to use the meaning of a conditional expectation to write answers even before you derive them. So they will guide you toward the answer. And this is, we will just try to evaluate this part in part C, basically to see how you can use so-called memorylessness property or forgetfulness property of exponential distribution. Did you talk about that before? Okay. So we will see actually, okay, maybe I shouldn't. Can you guess? Actually, we have a nice formula for this one as well. For this case. Now I know that this is given by this. Then in part C, the question is what this looks like if you know x1, right, has exponential distribution with rate lambda 1. Right? Namely this. Any guesses? Obviously, this should be larger than A. Right? We concluded that. But any ideas? It's a simple form. Expectation of x1, which is 1 over lambda. Huh? Right? It is an exponential random variable. Its expectation is 1 over lambda. So you are suggesting it is 1 over lambda? Well, how can you make sure that this is bigger than A? I didn't say anything about lambda. A should be part of the answer. But it is actually the simplest thing that can happen. A plus 1 over lambda. How can this happen? Right? So it is as if you are paid A, and then on top of that, you are getting just the expected value of one of this. Does that make sense? This has something to do with the forgetfulness property. What exactly is happening is, okay, given that x1 is greater than A, you know that you will get A plus something above that. But since x1 has exponential property, condition on that it is already greater than F just forgets that it is actually additional. It just behaves as if you are adding on top of a brand new random variable, x1, which has the same distribution, exponential distribution. And then you get all of a sudden not the conditional expectation, but unconditional. Right? We'll argue that. So, but when you have an exponential, right, condition on that x1 is greater than A, right? So we can write this x1 first of all, A plus the excess over A, excess over A. The excess of an exponential over A, given that it is already bigger than A, will have unconditionally exponential random variable because it just forgets that it is actually the tail. And A comes right away, and this has exactly the same exponential distribution with the same mean, so you add that. All right? We'll write it down in detail. But okay, what is this? Okay, that's fine. We will write it down, but okay, let's start with this one, right? We took care of this, and let us look at this. How can an unconditional expectation take such a weird form? All of a sudden you get a conditional expectation. Well, you will just follow the definitions, nothing more than that. So, okay, this is part B. So for A we have an answer, and here, right, just as before I take expectations, I'm just going to study the random variable itself, right? Then we will take expectations. If necessary, we will look at the probabilities. So what is this? What is this? Well, we said n is finite, right? While this is happening, right, actually there is a 1 here that multiplies. That 1 is, that can be written like this. Okay, so I'm not going to write it here. So these are the same things. Why is it? What happens if you sum all these indicated random variables from 1 to infinity? What does it mean? So this is the indicator of the event that you will sell the asset at time n. It is when you will eventually sell the asset anyway. We know from here. What this says that this is the indicator random variable of actually the event that n is finite. Which is in English, what is it? You eventually sell the asset. Which happens with probability 1. So this sum is 1 in fact. Right? Why did I just took a more difficult way of writing a single simple 1? Well, actually you can just put it here. Right? So you are actually interested in the value of xn, but it is easier to think what it is when you specify further when exactly you sold this asset. So on this event, you know that you sold the asset at time n, then of course the value for which you sold this asset equals to the bit you received at time little n, right? It's as simple as that. Maybe it is easier to just look at it like this, if you can see what is going on, right? The value of asset, or the value that you will be paid is, of course, the value of bit that you received at the time you sold it, right? That's the statement, nothing more than that, right? So we have that, and we will just elaborate more about this. So what does it mean that you sold it exactly at time n? That means you have not sold it at time n minus 1. Why? Because the bit was small. You didn't sell it, of course, at time n minus 2 for the same reason, right? Actually, right, we can then write all these things in terms of the values of the bits rather than this silly letter. So you sold it at time n because at time 1 the bit was strictly less than a. Is it strict? Less than or equal to I? At time 2, same thing happened. Well, at time n minus 1, the bit was again less than or equal to a, but when time n comes, the bit turned out to be strictly greater than a, therefore you solve it. Right? Right, just the way I wrote one in a complicated way, right? I again wrote a simple event, a more complicated way. You may think it like that, but we have to do that because we know more about x's than n. So therefore we have to just take this pain to develop some identity. But what is it? It is again just a simple intuitive argument. I am not even talking about probabilities. You see, it's actually I take a random variable, a function. I find an equivalent way of writing it, right? And then we will take expectations. I guess this is a good. Is this a good place to take the expectations? Let me try. Now, if two random variables are the same, then their expectations must be the same. Right? So the expected value of xn is the same as the expected value of these guys. But what is the sum of bunch of random variables? So expected value of the sum is the sum of the expected values. Right? The sum from 1 to infinity of expected value of these guys here. So you have xn times what? The indicator of the joint event of these random variables involving these random variables, right? Right. Now our lives is a little easier, right? Here I don't know what even the distribution was. Here I have x. It's just for a fixed time. It's 4, for example. Right? For that I am trying to calculate the expected value, right? But then there is this random variable, well, indicator random variable, right? That and a bunch of random variables as well. But now remember, we still haven't used one piece of information over there. We are told that these random variables are independent of each other. So you have a bunch of random variables multiplied to each other. The product of independent expected value of the product of independent random variables is going to be the product of expected values. So we can just use that idea to simplify this. So before you take the summation, look at this one. Where is the product? Well, I can see only 2 here, right? xn times indicator. But there are more, right? Because the indicator of the intersection of events. You have a bunch of events intersected with each other. So this is nothing but, well, in the meantime, I would like to just gather similar random variables together. So there is xn here. Also there is xn greater than a here, right? So let me just take that indicator closer to xn. So inside expectation, first of all, you have xn times xn greater than a times, then we can just follow the same order if you wish. Indicator of the event that x1 is less than or equal to a times the indicator of the event that x2 is less than or equal to a. It goes like this till when? I guess the only thing that is left is xn minus 1. xn is over there. Right? What did I do? Sometimes I write the product of indicators as an indicator of a single event, but sometimes it pays better if you just write one single indicator or indicator of a single event as the product of events. Why is that? Because now to calculate this expectation, I need to calculate this expectation, right? And okay, let me just write everything so that we don't lose track of the main question. So we have that, right? And then again, we'll forget for a while the summation and look at the term inside, right? So now this thing, right? So this thing, right, depends on the xn, and this thing depends on the x1, therefore they are independent. And this depends on the x2, and this depends on xn minus 1. All these guys are independent of each other. Because functions of independent random variables are independent. right? Xn and indicator of the function of the event xn greater than a are not independent because they depend on both the same random variable xn, right? So if we use just the independence, right? Independence of x1, x2, and so on, then I can write that expectation as the expected value of xn on the event that xn is greater than a times the expected value of the indicator of x1 is less than or equal to a times, it goes like this, the expected value, right? So these are all individual expectations. Xn minus 1 is less than or equal to a, right? And then, do we know what they are? Well, this is what? This is again the expectation of a Bernoulli random variable. Success probability is what? The probability of the event. So this is f of a then. Because x1 has what? Oh, forget about f of a. I don't like f of a. That's because I still need to use other stuff. So this is, I will explicitly write it. It is just the probability of a1. And what is this? The expected value of this Bernoulli random variable is the probability, success probability of the same Bernoulli, which is the probability of the event to which indicator function indicates, right? Can I do anything about this? Perhaps not. It should just stay as it is. I don't know how further I can simplify that. It will just stay. But, okay, let me write here. So here we use independence of random variables. But we also know that they are identically distributed. They are identically distributed. That means, since this is only an expectation, this number is the same if you replace xn with x1 everywhere. Right? Because they have the same f, cumulative distribution function. The same density function. For expectations, what do you do? All possible values of xn, right? For all possible values of xn, you just calculate this value, multiply with the probability with which that random variable xn takes that value. Well, that's the probability mass function, which is the same for x1 as well. So these numbers are the same. Here, well, okay, this is probability of x1 less than or equal to a. But, for example, this one is again the same, right? So this is the same as the probability that x1 is less than or equal to a, because xn minus 1 and x1 and anything else in between all have the same distribution function. So in fact you have the same number multiplied how many times? N minus 1 times. Exactly. Now you look at here now. Well, it is a sum over n, but n appears only there and nothing, nowhere else, right? So there you saw n was there, but we then concluded that because xn has exactly the same distribution of x1, this really doesn't depend on it. And each one of them are also individual, doesn't depend on n, but you multiply all the same number, n minus 1 times. Therefore, the only dependence on n comes from there. From the fact that you actually multiply the same number n minus 1 times. So therefore, you can just take this on, this expectation, right? It doesn't depend on n, but then you have the sum, right, of one number, okay, x1 less than or equal to a, to the power n minus 1, and you sum from 1 to infinity, right? What is this? A number between 0 and 1, right? You take powers and then you sum them up, right? You don't like 1, you can subtract 1 and then therefore you add 1. So this is like what? From 0 to infinity, there is a number between 0 and 1, you just raise the power and then you sum them up. This is just a geometric series again, right? It's geometric series, which is, we all remember this thing, right? So maybe you did not use much. So you have a p to the power n, and from 0 to infinity is given like what? 1 over 1 minus p. That's just applies when p equals that probability. So you have this unconditional expected value. And now this is 1 over 1 minus the probability that x1 is less than or equal to a. Right? We have a much simpler answer. Right? But then you also note that this is nothing but the probability that x1 is greater than a. It is 1 minus, it's just the probability of the complement. Right? Therefore, we can actually write this as a quotient. In the numerator, you have unconditional expected value, that expected value of x1 on the event that this bit is a good one, namely bigger than what you expected to receive from the market, and you divide by the probability that actually you will receive a bit, a satisfactory bit. Right? Like that. Does this look familiar? Huh? Huh? Have I already lost you? Huh? And that looks like this. The same event A, right? It appears both inside expectation. It is here. Unfortunately, A are the same, but A's are the same, but they mean different things. So we have this, right? So this is the event, this is the event. This is, by definition, if you just apply that, now this is x1, conditional expectation of x1 given that x1 is greater than a. Huh? So you have two choices then in an exam. Either you should be able to argue intuitively that this is true, right? Which is not that difficult, I guess. Or you will just take the pain and derive this. Huh? Was it difficult? Huh? But that's why you are here. So we are teaching you how to deal with this thing. So it's, if I were talking about what you already know, then this course wouldn't be exciting. Huh? Okay, we'll learn more. So I picked the difficult exercises so that you can see actually how you should approach to the problem. All right? Don't get discouraged with the whatever it involves to solve the problem. But do we have any questions? Maybe that might help a little. Is there any point that you found unintuitive? Why one would actually do such and such silly things? How would I figure out that I should have actually, I must basically take that step? Huh? If you look at this, what did we do? If two random variables come together, that's difficult. So what do? You actually split it into cases. That's how you split into cases. Right? If n equals n, then okay, this is something easy. Right? It's x little n is easy number. Right? But then you ask, well, this is too abstract for me. What does n equals n mean? Well, then you remember how you defined n. N was the first time you meet a guy who is willing to offer you a good price. That's exactly what you write here. The first one, no, you didn't like that, right? Second one, oh no. And the xn minus 1, no. But then the nth one comes and gives the price, right? So that's exactly when you decide to sell, right? So is there anything difficult in this part? The difficult part is just to get the habit of thinking in terms of these events, right? And you will just ask, like actually you are translating a contract, right, to somebody who doesn't know too much about selling or buying things, right? Okay, this is what you get. You get it only when you meet the right person, and at the time you meet the right person, of course that's what that person is going to offer you. That's it. There's nothing more than that. Then the rest is just a routine exercise. The expected value of the sum of random variables is, of course, the sum of expected values. That's the first thing that you have learned. Right? Well, you looked at this one. This is a bunch of random variables multiplied to each other. How do you see that? Well, I hinted you, right? From the beginning, I said the most important random variables in this course are going to be the ones, the indicator random variables, and nothing else. So whenever you see an indicator of if several events intersected it together, right? So you write that indicator, right away is a product. Now you have product of a bunch of random variables. And the good news is they're independent. So the expected value of the product of independent random variables, you just start multiplying expected values. So a bunch of expected values all multiply. And then you use what? Now you will just ask to yourselves, what are the values? Then you realize when you ask that question, okay, what is this and what is that? Then you say, well, they are the same. So they are the same because they have the same distribution function. And then you multiply all those numbers. This doesn't depend on n, but n is there. When you notice this, when you come to this point, you say, okay, this n also redundant. Actually, I can just get rid of that and put 1 there. So that the summation is now over n, and the expression depends in a very simple way. And then you only need to remember this formula, right? So you didn't remember this before you came to class, but now you cannot forget it. It's that simple, right? Okay, then you have that. We plug this one, and this is maybe new, right? We define conditional expectation in a not so intuitive way, although it is, as I said, the most useful form. Of course, I mean, people who developed this theory did not start with this formula. They actually went through all the difficulties of just learning, teaching these problems, and later they concluded that, okay, we have to start with this one, so that life is going to be easier. But at least, as you write the book, but I understand that it is not like that as you are trying to learn. As we do more exercises like this, I hope that you will get the same ability to think about these problems. Okay? Do I have to go through one more time? Huh? Do we have any questions? This is a good time to ask questions about this thing. So this actually, the exercise summarizes a lot of concepts that we covered by now. We saw again the indicator random variables, how they are composed, how do you use independence to write expectations, how do you use again indicators to simplify things. If you ask me, of course, I don't know. Right? And then we also use actually a practiced definition of a conditional expectation. Huh? No questions? Okay, that's great. That means we are comfortable to some extent. Okay. So this was the we now know why this equality is true, right? The bid, on average, the payment is going to be given by this. Then how can I just evaluate this one like this? How do I know that that expression equals A plus the mean of a typical bit if you know that bit as an exponential distribution? Let's look at that. Let's look at that. So part C. Okay, we are now told that these are not only IID but also have exponential distribution with some rate lambda, right? Okay, then, right, a bell rings, and then you remember all of a sudden, okay, exponential, these guys have exponential, forgetfulness property. They forget things. Now, in exactly which way do they do that? Well, the way we define it is like this. Take the first one. It is true for the second one because they are identically distributed. Conditional probability that x1 is greater than x plus y, given that x1 is already greater than x. You tell a guy that you are x centimeter high, right? And then you ask, what is the likelihood that he is even higher than that, right? Guy forgets instantaneously what you have just said, and it says, okay, it's the probability that x1 is greater than 1. Right? So this happens only for the exponential random variables among all continuously distributed random variables. It uniquely defines exponential. Right? But why is this true? Well, just to remind you, right? So x1 takes values near dy, not dy, let me use x. So what is the density function? It is given by lambda times e to the power lambda x dx. Right? Now, are you familiar with this notation? Did Korhan introduce this? Huh? Okay, right? You remember that. So density function. So you take an x and intervals with length dy, dx. So this is nothing but the probability, this is approximately the probability that x1 lies in this interval from x to x plus delta x dx. Right? So we know that this is the integral of the density function. If you call it f, you integrate that density function from x to x plus dx. Right? So it is this area. Right? And what do we know from calculus? Well, if dx is small, very small, it's tiny. If it is tiny, then you can approximate this area with a rectangle like this. So I already reduce the size to dx, right? Very small, right? So that this bump here, right, this curve will just disappear. It will look more and more like a straight line, right? Then calculating this area is well approximated by the area of rectangle, whose area can be found like what? Height times width. And the height is going to be around f of x, right? The value at x times width, what is it? Dx, the interval, right? So when we write like this, what you should note is this is the function under which you are supposed to calculate the area in order to find the probability, and you have to integrate. Now, why do we write like this? This is the closest to writing in the case of a discrete random variable to this. Right? For discrete random variables, you are allowed to write such things because they have positive probabilities. For continuous random variables, this is always 0. Okay? It's just a matter of notation. It's more than that, actually. Right? Probability that a continuous random variable equals x1 is just integral of density function over the interval from x1 to x1. It's just a one-point interval. Of course, the area is 0 because the width is 0. Okay, height is positive, but width is 0, so the rectangle will disappear. But when you write like this, x1 is in the neighborhood of x. That's how you read this thing. Then people understand that you know what you are talking about. If you write like this, they will fail you in the probability class. So you don't do that, right? So for continuous random variable, but the idea is exactly this. It's just the area, right? So you take fx, you multiply, you take the I, you multiply with the v. But other than that, all the formulas that you know for discrete random variables can be used with this formula right away. Expected value of x, right? In the discrete random variable case, it is sum of x times probability x equals little x, if it is discrete. For the continuous, you just replace sum with another sum. Why do you use this symbol? What does it stand for? It stands for letter S, which comes from sum. All right? Actually, you are still doing a summation. I don't know why people distinguish these things. You don't really have to do that. X remains like this, and instead of this, we said this is forbidden, but this will do that. You write like this. So I just transformed the definition of expectation for a discrete random variable to a continuous for a continuous. I adapted the definition for a discrete random variable for continuous, but in a very simple, by just basically copying the same operation, right? And here now, you will just remember, okay, for a exponential random variable, in this case, you are just required to replace this with the right-hand side, which is lambda e to the minus lambda x dx. And now you are familiar with this thing. You will just integrate and you are done, right? Something like that. So that it is very useful to think in terms of this, right? We'll see again examples. You will see me working with these animals in the remainder of this class. Anyway, let's just go back to our, okay. Well, for example, we can use now this to calculate. Apparently, I need to calculate this, right? Just to convince you that the exponential random variable has a memoryless property. What is this? Well, if this were a discrete random variable, then this would be like the sum, right? From sum over x starting from y all the way up to y of the probability that is x1 equals x, right? X is the dummy variable. That's the discrete version. And the continuous version, you replace this sum with integral. It is again a sum. We said it is s. Right now, and this will just turn into x1 in the neighborhood of x, right? And the sum, of course, from x equals y to x equals infinity. That's also possible to write, right? They are the same formula, nothing new, right? Then you, of course, copy this, right? So let me just go on from here. So from y to infinity, you have to integrate what? Lambda times e to the minus lambda x dx. Because that is, I was told that the probability that x1 almost equals to dx is given by this, right? Okay, and then what happens here? We'll just integrate. What is the integral? You don't remember? That's fine. It is. I am going to tell you what it is. It is this. Right? In probability theory, actually, we don't take integrals. We actually use cumulative distribution functions and the relations like this to complete randomly. You will also see that. Actually, it is quite interesting exercise. Okay, we have that. So let's just verify this. Left-hand side, what does this look like? Well, it is one event condition on the other, right? So we know that this is given like what? It's given by a quotient, and in the numerator you have the probability of joint probability of both events, and you divide by the probability that x1 is greater than x, right? Like this. And then, okay, let me just continue from left. So x1 is greater than x plus y, and at the same time greater than x1. What is this? No, x. Of course x. What is x? It is x. If x1 is greater than x plus y, of course it is greater than x, right? So both x and y are positive. I shouldn't forget to write that. Right? If x1 is greater than 4 plus 5, it is of course greater than 4. Right? Because it is already greater than 9. Right? So in this thing, you have only the first. x1 is greater than x plus y divided by the probability that x1 is greater than x. Okay. And did I already calculate this probability? Well, of course. x1 is greater than y is given by this. Replace y with x plus y. So you get e to the lambda times x plus y. And here, to get this, you replace y with x to get the formula for that, which is this. And well, there are cancellations, right? You get e to the minus lambda times y. But then, well, that's the right-hand side of this expression. Namely, this is nothing but the probability that x1 is greater than y. Am I right? Right. So that's the formula. This is a story told for a lamp, right, in the ceiling. You tell the lamp that, okay, you are running already for 4 hours. What is the probability that you will be around for 4 plus 2 more hours? this lamp, if it has a lifetime exponentially distributed, it forgets that it is already online for 4 hours. It just thinks that it is actually just put on the ceiling afresh, and it says, okay, I am as good as new, like actually I haven't run before. I will be running, I will be around in the next 2 hours as if I have just been placed in this place. All right? Forgets about its life in the past. Therefore, we call it a forgetfulness. And therefore, it is a little silly to use exponential distributions to model the lifetimes of objects like a car, a lamp, and things like that. But there is a reason why we use them. We will learn that later. Now, did I tell the entire story? No, I only explain you the forgetfulness property, but I still have to convince you that this is true, right? Okay, let me give a break. I already steal your minutes, I guess. Okay, 10 minutes later we'll be here.